You have character animation data with issues with your feet that are sliding on the ground and you want to fix those? Hi, I'm Jerome, and today we'll be looking at the Footskate cleanup for motion capture editing, a paper from 2002. As always, the first thing I will do is importing all the libraries I will need inside of my notebook, and I will load my characters as I'm doing every time. Now, one thing I will do on top of this is creating a new mesh, and that mesh is just a little target that I can place on the ground to display where I want to do some contacts. So just creating a new mesh. Now I will need to change a little my skeleton because the paper itself assume that you have this skeleton. Basically it needs to have a heel joint and a ball joint. And that's because they need to be able to know where the ground is relative to your ankle. And in my skeleton, I don't have those bones yet. So what I would do is inject the new bones. So I'm injecting the new bones here inside of my skeleton as child of the foot. And now that I have this, I actually have the same skeleton as what they want to have. And now that I have the skeleton, I can actually load my animation on top. And what I will do is that I will load the animation once as the animation I'm retargeting, and that's the reason why my feet will be sliding. If you check the video about the animation data, I explain why that's happening. It's because my characters has different proportions, so the feet would be sliding. And now what I will do also is I will import the original animation data as is, with the character squashed, but with the actual position from the animation data. And the reason why I'm doing this is because the paper itself is there to fix your feet on the ground when you know that the feet should be locked. Basically, it doesn't help you to detect when you want to lock the feet. It's allow you to compute it properly, but not the when. So luckily enough for me, the data from the LaFan database is actually extremely stable. So I will load the animation as the original data, and I will use just the position of the bones and the speed of the bones to know when I want to get the contacts and when I want it to move. So what I do is that I load twice the animation, and then my character is a little bigger than the one from the data. So I'm moving the character up a little. So it's a little bit off the ground. Otherwise the feet are really in the ground. Now, as I said, I want to compute when I want to get the contacts. And what I will do is that I would build a big buffer with all the contacts for every frame. So I have a buffer which has the frame count and then 4 values, and those 4 values are the left heel, left ball, right heel, right ball, contacts, basically when it's static or not. And I'm just using the extract feed contacts, which is just using an heuristic on the speed, and I'm checking the bone itself, and if the bones from the left heel is moving faster than 0.04 centimeters per second or something. I don't remember exactly the speed itself, but basically if the speed is lower than that, I'm assuming that there is a contact, otherwise it's moving. Now, what I do after is actually smoothing the signal a little, because it happens that you have a contact and then for one frame it turns off the contact and that kind of stuff. And I want to make sure that if I have just 1 or 2 frames that says I'm not in contact, it probably means that it's just a bug in the detection. So I just want to smooth the signal and make sure that I will always have at least 3 frames of contact. And that's what these little smooth functions are doing here. So now I can have my contact timing, and then we could display exactly what this means here. And so what I have is the animation moving, and then you could see when I've detected that I want to have a contact, and that's thanks to the original motion. And you can see the feet themselves are sliding compared to where the contacts are. At the bottom I have the signal on off for left heel, left ball, right heel, right ball, basically. Now that we know what the contacts, when the contacts should happen, I can actually go through the paper and see what the algorithm is. So for the Footskate cleanup methods, they basically have 5 different phases. And the first phase is to determine the position of each constraint. So to compute the constraint position, what the algorithm will do is compute it one bone at a time. And what you do is that if you detect that the heel should be static, what you do is you go forward in time and then go for L1 frames. So it's a constant. You could change and tweak how long that window of frames will be. But then what you do is that you go forward in time and you check every frame as long as there also says that they are all in constraint. You take the average of all those positions. So you get all the positions, take the average, and you drop it on the ground to get the contact on the ground. And for every other frames, if they says I'm in constraint and the frame before was already in constraint, basically I already computed the average, so I just keep the same constraint as the one from the frame before. You do this for each of your bones, and the only thing that will change is if, for instance, the ball says I'm in constraint for the first time in this frame, you will check if the heel was already constrained. And if it's the case, basically you reproject the distance of the ball, so you don't change the relation between heel ball, the distance between the heel ball. So it means that if you complete the heel first, you put the heel on the ground, and then the ball says, now I'm also constrained, you put the ball on the ground and you move it to keep the same distance. If you do the opposite, it means that you get the ball first on the ground. By the time you hit the heel on the ground, you actually move the heel to realign the distance also. So that's what I'm doing here. I'm computing the contact position. And the difference I have is, so I've used the L1 as a 10 frame, and I will build a big buffer with all my constraint position buffer. So it takes all the frame count, the position for the left heel, left ball, right heel, right balls, and then the XYZ position for the space. And I'm doing the entire buffer at once because basically I know the length of my animation. I can compute the entire animation in one go. The algorithm basically says that you could do it this way, or you could do frame by frame and recompute everything, or you could just try to build a bunch of buffers that have just the right sizes. It's easier for me to implement this paper by just saying, well, I'm doing the entire animation in one go. So I get a constraint buffer, the position buffer, and see, basically that's what I'm checking here. I'm checking if the constraint was, if the object was already constrained the frame before. In that case, I just keep the same position. Otherwise, I move forward L1 frame and I do the average and I drop it on the ground. And I do it for each, and I also reprojecting the distance, and I'm doing it for each left heel, left ball, and so on. So now that I've computed this, I can display what I will have here. And basically now it's the same as before, except that the position you could see here for each targets, they actually properly match where I will want them as the average of all the positions, and basically the distance between heel and ball are respected every time. The second part of the algorithm now is to compute the ankle position and rotation you will want to apply because of those constraints. Again, to compute that ankle position and orientation, you have several cases that can happen. And the first case we will cover basically is the case when we have a double constraint. So basically the heel and the ball are constrained. That means that now we could actually compute exactly where the ankle should be, because that's the simplest case. I have a fully constrained foot. I can compute the ankle, the orientation of the ankle and the position of the ankle. Now, if you have a single constraint, so meaning that maybe you only have the heel that is constrained, or maybe you only have the ball that is constrained, the only thing you have to do is not compute any reorientation of the ankle. You only want to move the ball, move the ankle to match the right heel, the right ball or the right heel position, depending on the context. So if you have a double constraint, you actually compute the position and orientation, and you have a single constraint, you only move the position. But that would work if you only have that single case. So if you only have always a single constraint or always double constraint, now you need to be able to transition from a single constraint up to a double constraint and all that kind of stuff. And that's what this explanation here is. It's about the fact that if for instance you compute a single constraint and you move your heel and it goes where you want it, and then the frame after is a double constraint, you will pop in that right position instantly. What you want to do instead is, when we compute the actual angle for the ankle, we don't save that information as an absolute value. We don't remember that it's exactly where we want the foot to be. We always compute those values as an offset compared to what the animation is. So if my animation says that my foot was here and I computed this position, I keep that information of offsets I would want to correct on the ankle. And then if I come from a single constraint, I can propagate that offsets back in time, and I can linearly blend that offset off. So what it means that if my constraint is here and my foot was here, the offset is that ankle. And so what I will do is that the frame before, I will also reapply that offset a little, but a little less. And then the frame before, I still add that offset, but a little less. So first thing you do is that you rotate the ankle back in time, you rotate the ankle, and then you move the foot. And it's the same if you have a double constraint and you reach a single constraint. The same way you add that offset and then you move the foot back, and then you add that offset and then move your foot back. And you do it back in time and forward in time. And then if you have that weird case when you actually go from double constraint back double constraint, you need to cross over that information, and that's the third case here. So again, ankle position and orientation. So I will have my buffer for the ankle rotation and the buffer for the ankle position for both left and right. And the first thing I compute is compute the double constraint. So again, that's easy because then I can just compute the constraint and save that information inside of my buffer. And if I have to compute the single constraint, what happens is we check if you have a single constraint. We then go back in time to see if we come from a double constraint. If it's the case, I do the slurp. So I'm lerping the amount of error I was doing because of the rotation. And same in the opposite way, if I will be reaching a double constraint, then I'm also slurping that stuff. And then the third case when I come from and go back to, I'm slurping the two slurps together. And then you get that final result. So that's basically what this is doing. And the only thing you have here is that weird formula for the alpha, and that comes from the paper also here. So basically, that's how they smooth the transition. They don't do purely linear correction. They do ease in, ease out correction, and that's what the formula allows you to have. And so I can compute my constraints. And now what I will have is my buffer here. I can display it, and you could see where I would want the ankle to be. And that's basically where every time you see there is a constraint, that's actually where I want the ankle to be when we compute it. So we've computed the orientation and the position of the ankle. We can go to the next step. And the next one is to compute the root placement. And the root placement basically means that, for instance, imagine that you try to fix the foot and you put it really far away from where the hips can be. Then you will have the issue that the foot cannot reach the constraint you wanted to fix. So what we will do is that we will move the hips. So we will make sure that the foot can always reach the position we want to do. And the root placement, well, basically, again, it depends on the case and how you want to compute it. If you only have one foot that is constrained, you could only, and it's too far, you could only move the root in the direction of the foot you're pulling. But if both feet are constrained, you actually need to compute the position here of where, by pulling on both feet, where the hips should be. And that's basically at the intersection of both spheres. So if imagine you have your foot and then you draw a sphere that is the size of your leg, and you do that for the second one. You have two spheres, and that means you have one point in the middle where you could put the hips that make sure that both legs can reach the position if the hips is at that spot. So that's how you do this. And basically, again, to avoid having your root that just pulls one frame when suddenly it cannot reach, what they do is that they average the position, they average the correction they will put on the roots along a bunch of frames. So this is what we do here in the root position. We try to compute the offset, compare both legs if the distance does not match, and then average the position of all those roots. And I have a buffer, so I will have a buffer of the root position now I would want to have. In my case, I can display where I want the hips to be. Basically, it won't change much because I'm actually never pulling the legs further than what the character is, because my character is actually bigger than what the original animation was. So I will never have the need to pull that root. Now, because of the average, you're not sure that you will always be able to reach that position, but that's not an issue. It will be fixed by the next step anyway. The next step is to be able to actually compute the IK. The way they have implemented that is to go through these steps. You do compute the angle thanks to the fact that the legs in this case will be a triangle, and then you could compute the angle you need for that triangle. So they do it in several paths. So you get the original pose, you don't move anything on that pose. Then you change the knee angle, and that's by computing this formula here. It's basically computing the angle thanks to the length of both legs and the length of the target you're trying to reach. So you basically compute a triangle and you try to compute the angle you will have at the knee. And then when you computed that angle, you rotate the knee. And now that you've rotated the knee, you could see the distance you have between where your foot would be and where the target should be. And you could rotate the entire leg to make sure that you are aligned with the foot. Then you realign the ankle to match what the ankle target was. And the last step they do, and they actually stretch the leg. And why do they stretch the leg? Because of two things. The first thing is that if you remember when we moved the root, we said that we were doing the average, which means that it's possible that your root is still too far for the leg to actually be able to reach it. So you do need to be able to stretch the leg because of the smoothing we did on the roots. And the second thing, it's when we try to do IK on that kind of stuff with the legs that really close to being stretched. What happened in IKs is that if your leg is really close to be straight, being straight or not will actually change the distance here really a little. So you might try to reach a point that are 1 or 2 centimeters away, and then it will be really visible on your knee. Usually we call that a knee pop. It's something that you could see when you do IK. You see that knee that moves really fast because it just goes from here to here just because it had to close a really small distance. So what they do is that they detect that the ankle is really close to be straight, and they allow the leg to stretch in that case, so they can avoid that knee pops and give more times for the knee to be straight. And I would do the same, except I will do a bit differently than the paper is doing it. I will not stretch the actual leg. I will just lock the angle of the knee. And I will just stretch by moving the foot relative to the leg, meaning that basically that deformation is absorbed by my ankle, and it's really not visible when you have a small distance. Seeing that the ankle is changing in size is not more visible than trying to stretch the entire leg and moving knees, ankle, and everything. So just by doing this, I mean, it's enough. And so what I'm doing is the part that you have here, all the Arcos formula, it's the one I'm doing here. So preparing all the different lengths compared to the distance, computing the vector, computing the Arcos, and then I'm taking that Arcos, and what I'm doing is that I'm putting it through a polynomial. I'll show you the polynomial later. Basically, just to make sure that my ankle would avoid having that knee pop. And then I can compute the angle, I can rotate the knee, I can recompute the position of the knee, I can rotate the entire leg, compute the global position of the foot, and then put back my ankle. So it's all the step of the paper. And I do the same for the right leg and all kind of stuff. And just to show you what that weird polynomial is, it's just this. So basically, we could see it's really close of a straight line, and that's an arccos basically means that is the inverse of the cosinus. So at -1, I have an 180 degrees. So my leg is really straight. And what I do is I have something that is nearly mapping, except here at the end. So the blue will be the arccos value, and my orange one is the functions that I'm computing. See that basically that means that if my leg should have been a straight line with 180 degrees, I'm just keeping a little angle in there, and that it goes further, and so you will always be able to make sure that you always keep an angle, and it's a smooth angle here. So at least I'm never have a straight leg, and I'm never stretching. So it's not exactly how they were doing it, but it's one way of having the not having the knee pop, let's say. I can compute my IK, so at least I have something to show. And now I can render what they had here. And then you could see that when the constraints are on, basically my legs are properly placed, my foot are properly placed where the ankle wanted to be, except that you could see pops every time my animation turns on and off. You get that pop for every constraint. And so that's actually the last step of the algorithm, is the final processing. And what the final processing does is, well, realizing that we've computed every ankle position and all of that as an offset compared to where the animation was. And if you remember what we moved from single to double, or double to single, we smooth out that information. And basically what the final processing would be doing is the same thing. It would say, okay, now we could detect every time a constraint is turned on and off, and we could also propagate the offsets and blend them in and blend them out the same way we did for the single to double, except now we do it for every constraint. So check for the ankle, make sure that we turn on and off, and then we blend that information also forward the same way. And then when we've done this, we can finally do the IK on that solution instead of doing the IK before doing the final processing. And now what we have is this. You could see that moving in and out of a constraint now is perfectly smooth because we've smoothed out that information. So we have exactly what we wanted. And this is one of the ways you could fix sliding issues. If you find this video to be too fast or too slow or not enough in detail, feel free to comment at the bottom so I'll know how to adjust for future videos. And I will see you for the next paper.